Okay, so today we are going to do some moment of inertia stuff, and we're going to kind of look at these problems that I kind of messed up a little bit. And the first thing that I want to do, these are the two problems we're going to do. Both of these are from practice, I don't know, number 10 or whatever practice number it was. And, the goal of them was, in the first one, the one on the left, it was to find the moment of inertia with respect to the x-axis. And the one on the right, it was to find Ix and Iy with respect to the centroidal axis. Okay, so we're going to do these, and we're going to do these in turn. But before I do either of these, what I want to do, because it's going to kind of inform how we do this, is I'm going to actually go ahead and solve for the moment of inertia of like just a rectangle. Because that will help me to kind of understand what I'm going to do here and what I'm going to do here. Okay, so let's move over here, and let's just do like some random rectangle. And what I want to imagine for this rectangle is that I want to find Ix. Okay, so I want to find Ix, and I want to do it two different ways. I want to find what is, the moment of inertia around the x-axis. And then I'm also going to do this where I want to find the Ix around its centroidal axis. Okay, and these are hopefully like, these should seem trivial, right? There's a chart in your book, and you're just going to go look up what the centroidal axis for these things is. Okay, but what I want to do is I want to imagine that we don't know what those things are. And so we've just got this rectangle. The only thing we know about it, the only thing that let's imagine that I give you, is that the base has some, width b, and the height has some height h. Okay, and from the part on centroids, we know where the centroid, well, let's not worry about the centroid yet. Let's find the Ix around the centroidal axis, around the x-axis. So that's relative to this axis right here. Okay, and so what I want you to remember is that the moment of inertia, let's just call it just a general moment of inertia, okay, is the integral of the radius squared dA. Okay, and so basically for all the little areas in this whole thing, we're basically going to add up their r squared. So what that means to me, okay, is that I want to find some small areas that have the same r squared. Okay, so what I'm going to do to find small areas that have the same radius is I'm going to create a little tiny box. Unfortunately, these boxes kind of look funny, but whatever. Okay, so here's a little tiny box. Oh, let me create it. Okay, and it's a little bit, out of place. So let's move it into place like that. Okay, now keep in mind that this box could have been anywhere. And what I want to do is I want to note that, okay, let's zoom in and let's look at this box. Okay, because I'm trying to get r squared and dA. All right, so let's see. So we've got a little, no, don't do that. Okay, okay, so we've got a little position right here. And that position is, it looks to me like that position is in the x direction, it's b, right? In the y direction, it's, I don't know, y. Right, now this position right here, in the x direction is 0, and the y direction is just some y. Okay, the thickness of this box right here, okay, well, that's going to be dy. Okay, so what we can do is we can say, okay, well, let's solve for this. Let's use this formula right here, okay, because the radius here, okay, so that's the distance between our box and the x-axis, the thing we're taking it around. So the radius here is this distance right here. So I can say r is, that distance is y, right? And then the dA, well, we need the area of that box. So the height of that box is dy, and the width of that box going from here to here, well, that's b. Okay? So I can create a formula out of that. If I go down here, let's go ahead and solve this. I can say, well, we're going to integrate. Come on. We're going to integrate. Okay, so I've got r squared, so that's going to be y squared. Okay, and then I've got d. So that's going to be b times dy. Okay? And that's going to go from, the first box is going to be down here somewhere, and the second box is going to be right here, and the third box is going to be right here. Now, we have infinitely many of them because dy is infinitely small, but you see they're going to start at y equals 0, and they're going to go until we get to y equals h. Right? So we're going to go from 0 to h. Okay? So the nice thing about this is b is some constant, right? So we're going to say, okay, well, that means ix equals, let's see, it looks like b can be pulled out because it's a constant, b. And then we're left with y squared dy. So we're going to change that into y cubed times 1/3, like that. And then we're going to go from h to 0. So the ix equals, let's see here, so we're going to plug in that h cubed, and we're going to get bh cubed over 3. Okay? If you look in your book, you will find that this is the solution for the moment of inertia around the axis. Okay? And that's how we do it. Okay? Now, similarly, if we wanted to do it around the, around the centroid, well, that's a little bit different, isn't it? Okay? So let's try that. Let's do this around the centroid. So first I'm going to get my little eraser. And we'll see if I can't just erase all these lines without erasing the box itself. It looks like they're going to let me do that. Okay. Okay, so we're going to do all of that. Okay, taking a little longer than we would like, of course. Maybe I should have paused the recording. But now we're going to go to some location. Come on, you can do it. Okay, right here in the centroid, right? And we know the location of that centroid is, well, it's going to be h over 2, b over 2, or excuse me, b over 2, h over 2. Okay? Now, already you should be thinking about this and going, well, this one's going to be a little bit harder, right? So it's the same formula as we had over here, okay, r squared dA, but our r is a little bit more difficult, right? Because our r is the distance from the thing that we want to take the moment of inertia around. So, so where the box currently is, well, let's see. So we want to know what this distance is. Okay, so the distance basically to this axis, right? Okay, well, we know this distance is h on 2. Okay, we know this distance is y. So this distance right here is y minus h on 2. Okay, so this is going to be y minus h on 2. That's r. Okay, so r squared is going to be that squared. So we could square that, square this. Okay. Now note that will also solve if y gets smaller than h on 2. That's fine. Okay, it's totally fine. Especially because we're squaring it, right? So it's all going to become positive. Okay, now we need the dA, okay? Well, the dA, luckily, is the same as it was last time, right? Nothing has happened to this rectangle to change the area, right? The width of it is still b, and the height of it is still dy. So we have a b dy. Okay, so let's go down here. Let's get our ix equals the integral of r squared, which is y minus h on 2 squared. So this is going to be y minus h on 2 squared. And dA, b dy. B dy. Now the last thing we need is our limits of integration. So we're going to go up here and we're going to, let's see. So again, we're starting at h equals 0 y equals 0. And we've got all these boxes and we're stacking them all up until we get to y equals h. Okay, so now we just have to solve that. Okay, and it's a little ugly. So, we have to FOIL that if you don't remember how to FOIL. And, if you don't, maybe it's been a while, so it's going to be y squared minus yh plus h squared on 4. Okay, and we're going to pull the b out because it's not necessary, it's constant. Okay, and then we're going to get the ix bar. Okay, b times, let's see, so this is going to be y cubed 1/3 minus h is a constant. So we're going to get y squared h on 2 plus this whole thing is a constant. So it's just going to be h squared on 4 times y. Okay, and we're going to take all of that from h to 0. Okay, note here that if you start thinking about units, we've got 3 lengths in each of these. We've got a y cubed here. We've got an h and a y squared in that one, so that's 3 lengths. And we've got an h squared y in this one, so that's 3 lengths. Okay, so we plug all this in. We're going to get I prime x equals b. Okay. Let's see here. This is going to be h cubed on 3 minus h cubed on 2 plus h cubed on 4. Okay, notice this is our original answer from over here. If we go over here, we got bh cubed on 3. That's this first bit, and we're correcting it. Okay. I haven't done the math here, but this ultimately is the parallel axis theorem coming to work here. Okay, so if you convert all of this to twelfths, if you remember all this from way back when, this becomes, this becomes a 12th. Okay, and so this becomes 4/12. This one becomes a 12th. So it goes from 1/12 to 6/12. This one goes to 12ths. It becomes 3/12. Okay, so 4 minus 6 plus 3 is a positive 1. Okay, so we end up with I x bar equals 1/12 bh cubed. Okay, and if you look up in the back of your book, you'll see that that is the solution for a rectangle around its centroidal axis. Okay, so we just want to be careful with these two. Okay, they're both correct, but the one on the left is around just, the axis at the bottom of the rectangle, and the one on the right is the centroidal axis. Okay, to use the parallel axis theorem, you need to be using this one. Okay, if you're integrating, and for some reason you have your rectangles perpendicular to the axis that you want to use, you need to use this one. Okay, we're going to use both of these moving forward in the rest of this lesson. Okay, and there's just going to be different times for different ones. Okay, so hopefully that made some sense to you guys. So note there's 2 axes here. This one applies to this axis right here. Excuse me. And this one applies to the centroidal axis, which is more or less right here. Okay? All right, so let's go over here and let's solve this sucker. All right? I love this guy. Okay? Now, we want to know, once again, so what's going to be important here when you work these is to note right off the bat which axis are you looking for. Okay, so for this case, the question, although I've kind of erased the question, but the question was, Ix equals question mark. Okay, so Ix. So it means, what is the moment of inertia relative to this axis down here at the bottom? Okay, now some of you might ask, well, how do we get at that? Okay, can I, how do I know I need to integrate? Well, the reason you need to know you need to integrate is this is in a composite shape. Okay, and it's a little bit blurry here, but that's a k e to the x over a. Okay, now normally what I suggest you do in this case is to create a rectangle. Okay, let me get my little rectangle tool. And to create a rectangle going like this. Okay, the reason I like that rectangle is because the formula for the moment of inertia looks like this. Any I equals r squared dA integrated. Okay, and every point in that rectangle has the same r. Okay, and in this, usually that's just y, right, or something, right? Usually it's pretty straightforward, not always. The problem with this is the dA for this particular portion of this problem is right here, right? So it's got a width of A, and it's got a height of dy. So it doesn't really seem all that hard, but the problem is that definition fails badly when we get right here. Okay, because once we get right there, if I draw my little rectangle, so here's a point right here, x comma y, okay, and here's a rectangle. Okay, I'm going to do my best to draw it right there. Okay, and notice that this also has a has a little dy right here. But the width of this thing, well, let's see. This right here is x. This right here is a. So this distance right here is a minus x. Okay, so the area here, so the dA here equals, let's see here, equals a minus x times dy. And over here, dA equals a times dy. Okay, pretty annoying, right? So what you end up having to do is basically you have to split this thing into two separate integrals along that line that I have right here, because you cannot define a single integral that's going to have all of this. So you basically end up having area 1 and area 2. Okay? And I think just because it's a good, exercise, we'll go ahead and do that right now. Especially because I've already defined the dx's. And the r's in this case are actually pretty straightforward. Let me see the dA's. The r's are straightforward. It's just going to be the letter y to here. Okay, where this point right here is, it looks like that point is a in the x and y in the y. Okay. And then up here, it's just, r, which in this case is the y right there. So, right. Now, the other thing we're going to do here to make our lives easier, though, is we're going to note that this thing on the bottom, well, this is a rectangle, isn't it? Okay, so if we get a nice rectangle like that, I can go ahead and get the ix of the rectangle, okay, by using this formula that we did over here, right? Because we know ix of the rectangle around its base is bh cubed over 3. Okay, so let's go ahead and do that. The base of that thing is a. The height of that thing, well, it goes up to this point right here, and we need to know what that number is, and then we're going to divide by 3. Okay, so what is that number? Well, I've got this formula right here, y equals k e to the x on a, and so I need to know what that value is when x is 0, right? Because right here I know x is 0, what's y? That's what we're looking for. So I'm going to take this equation right here, y equals k e x on a, well, 0 over a. Okay, anything raised to the 0th power is 1, so y equals k. So this is k. Okay, so that is the height right here of our rectangle, a k cubed. Okay, so this is half of our problem. So we don't know what k is yet. Well, I guess we'll have to figure that out at some point. We might as well figure out what k is right now. Let's go ahead and figure out what k is. All right, so if ever you get a problem like this and they want you to figure out what k is, okay, the way to do this, okay, let's figure out what k is. So let's, come here. Come on, you can do it. Okay, what we're going to do is we're going to go up here, and I know this point right here. The value of that point is a comma b. Okay, and I know it's defined, it satisfies this equation because it's on that line. So y equals k e to the x over a. So we're just going to start plugging some stuff in here. So y is b. K is what we're looking for. E to the x, not x, right? We're plugging in a over a. A over A. So that's e to the 1, which is just e. Right? So k, k is an ugly number, isn't it? So k equals b over e. Okay? That's not really an answer we wanted. I think we can all agree that that was not the solution we were hoping for k. We were hoping that k would just come out to be something nice and pretty. Okay, but it doesn't matter, right? It's just annoying, but it doesn't matter. So let's go ahead and plug it in down here so we can get that going for us. So we get a b cubed over 3e cubed. Okay, whatever. It doesn't mean anything to me, which is kind of annoying, but that's just the way it goes. Okay, so now that we've got that, let's go ahead and let's try to clean this up a little bit if we can. Well, I guess we don't really need to, right? Because we already got our dA for this top bit. Okay, the height of it is dy, and the width of it is a minus x, which is this distance right here. Okay, and the radius of it is just going to be y. So for that bit, we're going to use our formula. So ix of the, I don't know what you want to call it, the little sliver, equals, okay, the integral of r squared, in this case that's y squared, dA is a minus x dy. Hachi machi. I have a feeling this is going to get ugly, okay? Now we're doing dy's, so we're going to go from k right here, and we're going to stack them up until we get all the way up there, where we're going to get a y value of b. Right, so we're going to go from k to b. Okay, but silly us, we're not going to get to use k, right? We're going to have to use b on e. Right, I mean, it's really not all that pleasant right here, but that's just the way it goes. B, come on, it's freezing on me again. B on e, b on e. Okay, now the problem when we integrate, if we have an x right here, the problem becomes, well, how do we deal with that? Okay, well, we have to have it not as an x. So if we go up here, this is our equation, and we need to solve that for x. Okay, I had really hoped to not have to do this. Okay, and I hopefully what you're seeing right now is that this is a mess, but let's go ahead and do it anyway. Okay, so we're going to get, so we got y equals k e to the x on a, and what we're going to do is going to make that y on k equals e to the x on a. And then how do we get rid of that? Well, we're going to do a little natural log action, which is going to get rid of this. Okay, and then we want to get x alone, so we're going to multiply both sides by a. So a natural log y on k equals x. Okay, I know, once again, I know some of you were really hoping for that answer. I know I wasn't. Okay, so we're going to take this nasty equation right here. Okay, we just don't like it, right? And we're going to plug it in down here. Okay, can you see how disgusting and difficult this is going to be? It's going to be very difficult, okay? We may not even solve this all the way. I haven't decided yet. Equals, okay, so we got integral from b to b over e of y squared, a minus, what's x in this case? A natural log of y over k, okay, dy. Okay, now again, I accidentally have a k in there. We don't really want a k, so we're going to make that b over e. Okay, so let's do this. Let's erase that k right there. Let's say make that b over e. Okay, probably most of you all are like me and don't really remember your log rules. But in this case, you can actually just ignore that e, okay, because it'll kind of split out and then it'll go away. So that's kind of nice. So we'll leave it like that. Okay, so you can see that this thing is getting quite nasty. Okay, iy of this little sliver bit equals the integral from b to b over e of, looks like we've got y squared. It looks like we can pull that a all the way out. Okay, let's pull that a all the way out, minus the natural log of y over b. Oh, no, there's another y squared right there, isn't there? Okay, forgot to distribute dy. Okay, now, so integrating that is going to require integration by parts. And so we could finish this, but let's not, because this is getting really ugly. Okay, you can integrate this by parts, and what you would do is you would just add this number to this number, and you'll get your solution. Okay, if you're working a test and you're getting something really ugly like this, it's possible you made a mistake. It's possible I made a mistake here. But what I would recommend to you is an alternate solution. Okay, and what that one is I'm going to go up here and I'm going to delete a bunch of stuff. And maybe I'll come back and I'll solve this this interval. I'll leave all that work there and I'll come back and I'll solve this at the end if anybody wants to watch it get solved all the way. But what we're going to do instead of doing all of this is basically, instead of having a we need to leave that. Instead of having a horizontal box, which of course is nice because like we really, really want to use a horizontal box. Come on, you punk. You can do it. Give me a little I, there you go, IX, the rectangle. Okay, there you go. Okay, instead of using those horizontal boxes, which we like because the formula for the moment of inertia is r squared dA. And what we're doing is we're adding up the moment of inertia of all these little boxes. Okay, each one has r squared over dA. I can do something else entirely. Oh, let's not forget, this is the axis we care about down here. Okay, this is the x-axis. Is instead, I can use a box where all the boxes are defined exactly the same. Okay, and it looks like this. Okay, it is the vertical box. The old vertical box. Okay, and then we'll go right in here and we'll say, okay, well here's our location. It's right on our line, so that's x comma y. Sweet. Okay. Now we can't use this formula right here though, and the reason is because this point has a way bigger r than this point, because we're basically saying how far is it away from here versus here. However, I can get the moment of inertia of that entire rectangle, right? So the moment of inertia of that entire rectangle. Okay, well, that's pretty straightforward, isn't it? Right? So the moment of inertia relative to his base looks like this sucker. Okay, maybe I can draw some more arrows around it. Okay, bh cubed over 3. Okay, so this is for a little rectangle. Okay, or basically, I think usually the way they draw this is they say, well, what is it for dI? X. Okay, so for that little box right there, it looks like this, right? Well, what's the base? So it's going to be base times the height over cube. Well, what's the base of this thing? Well, it looks like it's dx, isn't it? dx. Okay, what's the height of that box? Well, it's going from here to there, so that's going to be y cubed. We'll divide that by 3. Okay, so you might say, well, okay, but how do we want ix for the whole thing? Well, for the whole thing, it looks like this. We're just going to integrate it. Okay, so basically I'm just going to integrate both sides of this thing. Okay, and I get y cubed. I'm going to bring that 1/3 out. Okay, dx. Now this is still annoying, right? Because I've got y cubed. Because I have to cube this thing right here. Okay, but that's a little bit more reasonable, right? Because I need to get the y here to match the x here. So we're going to say, well, let's see here. Ix equals 1/3 integral. Oh, wait, I forgot my limits, right? We're going to start over here at x equals 0. And we're going to keep going with all these little boxes until we get over here where x equals a. So we'll go from 0 to a. And well, what's y cubed? Well, that's going to be k cubed. K cubed. E to the 3x over a. Okay. dx. Okay, hopefully right now you're already seeing the thing that we don't like about this, which is that k cubed. So we're going to replace k cubed with b over e, because that's what we discovered earlier, that k is. So it's going to be b over e cubed. Now, if you're hoping that e cubed on the bottom is going to sort of cancel out with that e to the 3 that we got right there, well, you're in luck. But it's not going to completely save us. Right, so we got to do some logarithmic rules. And so we're going to get a b cubed e to the 3x over a. And then we had an e cubed on the bottom, so we got to subtract 3. Right? Achi machi. That's not what we wanted to have happen, is it? Well, I'm sorry, guys. But those are the rules. Okay, ix equals. Okay, and then let's see. We still have this integral from a to 0 and dx. And I think at this point, we're ready to integrate, even if we don't like it. Okay, so actually, I'm going to make one more simplification here. I'm going to simplify these things here. I'm going to pull the 3 out, x over a minus 1 like that. Okay, it's not critical. Okay, so let's do this. I'm going to zoom in so we have more space, because now we're just doing some math. Okay, so 1/3. Okay, the b cubed can come out because it's a constant. Okay, now we've got e to the 3x minus a over 1. Do you remember how to do e's with derivatives? They're actually kind of nice. And we'll integrate e to the 3 blah, blah, blah. So if you remember from calculus class, the way you do this is x over a minus 1. And then you have to take care of the chain rule. So normally e to the 3x over a minus 1, if you were to take the derivative of that, you would get the same thing. And then the chain rule in this case would be 3 over a. So we need to deal with that. And when we integrate, so it would be a over 3. A over 3, like this. Okay, and then we'll do all of that from a to 0, like such. Okay, so, well, that looks like a 9, doesn't it? Go ahead and plug in the a here. We can make that an a. Okay, so we'll say ix equals, well, it looks like ab cubed over 9, ab cubed over 9. And then over here, well, 3 to the, let's see here, a over a minus 1. So that's 1 minus 1, so that's e to the 0. E to the 0 minus, now if I put e to the negative 1. Yachi machi. I think that's right. Yeah, so we plug in a 0, we get e to the, oh, negative 3, isn't it? Sorry, my bad. Right, so if we plug in 0, this term goes away, and we get e to the negative 3. Achi machi. Okay, so 1 minus 1 over e cubed. All right. Okay, so at this point, I think we'll go into our calculator, and we'll punch it out, and we'll get ix equals to 5 sig figs. It looks like we get 0.10558. 558 AB cubed. Okay. Once again, the only thing we really want to check here, because I have no idea if this is a reasonable number or not, but we want to check to make sure that we got length to the 4th, because if we don't, then we've made a mistake here. We've got a to the 1st and b to the 3rd, so that means we've got length to the 4th. Okay, so this number then means if we go down here, it's this answer right here. Okay, that is the correct answer. I know because I cheated because I'm a teacher and I have the manual. Okay, so basically the ultimate point of this, I mean, we don't always have an expression that's as difficult as this one, although we may, right? Because I have to do some tricky things to keep you guys from being able to just look this stuff up on the internets. Well, not tricky, but some not as easy as I'd like it to be. But anyway, so there it is, and just be careful with that stuff, okay? But the point here is, if you get an unusual thing where, like, notice in this case, for the top half of this, if I went with horizontal boxes, right, that is a different horizontal. That horizontal box is defined differently than the one on the bottom. So you might just want to go with a vertical box, and if you use the vertical box, then what you're summing is you're saying di equals the base of that box, which in this case is a dx, times the height of that box, which in this case is y cubed, okay, over 3. Okay, And so that's all from the fact that I of a rectangle around its base, around x, is the base times the height cubed over 3. Okay. Now the same thing would apply if we were doing around the y-axis, right? Okay. So just be aware of that. Okay. So anyway. So that's really the way that we use this particular formula right here, and that's where it kind of shows up for us. Okay, now where does this one show up? Okay, this one shows up with the parallel axis theorem. So I'm going to go over here to this one. Okay, so this one right here, this one wants Ix around the centroid and Iy around the centroid. Okay, now just because it's quick, I'm going to go ahead and imagine that this is one giant rectangle. And that way I can figure out Ix and Iy for this if it were a giant rectangle, because I think that's a good way to kind of get an estimate of our thing. So let's do Iy bar, okay, if no hole, or whatever you want to call it, okay? So if this whole thing were filled in, right? This all looks a little janky. So this number right here, let's say is 3.5 inches. I don't, I didn't create this image. It just came all ugly. Anywho, so in this case, Ix bar, if no hole, equals 1/12 of the base of this thing times the height of this. 1/12, the base of this thing times the height of this thing cubed. Okay? It's like the simplest problem ever. Okay? And the way I solved it earlier was with a capital B and a capital H. We could leave it like that if we want. Okay, so it's going to be 1/12. What's the base of this sucker? Well, it's, it looks like, so it's 0.9 inches plus 2 inches plus 3.5 inches. So what's that? 5.4 inches? 5.4 inches. Okay, times the height cubed. Well, that's 1.8 plus 5 plus 1.2, so that's 8 inches cubed. Okay, Ix bar, if no hole, comes out to, let's see, clear on 230.4 inches to the fourth. All right, okay, so that's a good estimate. So with that hole, I should expect this thing to be a little bit easier to bend. So I should expect a smaller number than that, and I don't know how much smaller, maybe in the 180s, maybe 200, maybe 150, I don't know. But certainly if I got a number like 2,000, or if I got a number higher than 230.4, that would be pretty unusual. So just be aware of that, okay? So I'm going to go ahead and do Iy bar, okay, if no hole. Okay, so if it was solid. And we'll do 1/12 of the base times the height cubed here. Okay, and Jeff Hansen, he likes to just use this BH cubed as the formula. I'm the same way. It's just that in this case, the base is this one. Okay, so it's going to be 8 inches. And the height will be this way, okay? And so that's going to be 5.4 inches cubed. And note that we would expect this number to be a little bit smaller because hopefully you can see that bending it around this axis would be a little bit easier than bending it around that axis, right? Okay, so let's go ahead and plug this sucker in. Let's use our little fancy calculator. And sure enough, it's going to be easier to bend, 104.98. Okay, and again, these answers are not important. These are just to give you an idea of what we should expect, right? We should expect our Ix and our Iy's to be smaller than this because it's the same thing. It's just like missing, we're just going to like remove a piece of it, okay? So just something to think about, okay? So now what we're going to do here is I'm going to go ahead and erase all this business because we don't need all these lines all over the place. But for some reason, some of these lines are a little bit more resistant to erasing than others. We need a more high-powered eraser. Okay. So what we need to do is first we need to discover where the centroid is, right? Because the centroid is moved. By removing that material in the middle, we don't have the same centroid. So we're going to have to get at that. Okay, so the first thing is we got to get the centroid. So now how do we get the centroid? Is we create a chart that looks like this. X bar, Y bar, A, X bar, A, Y bar, A. Okay, And we need to number these shapes. And you could break this up into a bunch of tiny rectangles, but I find it bigger, easiest to just do one big one and a negative one. Okay, so here's shape 1. Well, luckily, we've already kind of done some of this work, right? I got a little ahead of myself, didn't I? Anyway, so for shape 1, the x-bar is halfway between, these two spots. So if that total thing is 5.4 inches, we're going to be at 2.7 inches. Okay. The y-bar is going to be halfway between here and up to the top. Okay, this is our origin, by the way. This is 0, 0. So it's going to be half of 8, so it's going to be 4 inches. Okay. The area of that whole thing is 5.4 times 8, so I got a calculator for that. And I get 43.2. And I'm going to go ahead and put inches squared out here because I don't feel like writing it each time. And x bar A is, we're going to take that 43, and I'm just going to fill this out. Okay, and so if you don't know how to do that, go back and watch the videos on how to get those numbers. Okay, so then we're going to go to area 2, okay, or rectangle 2. And that's this little one right here, and it looks like it's 2 by 5, right? So let's see. So its x bar is going to be, it's going to be right in the middle here. So that's 1 from here to here, and then 0.9 from here to here. So it's going to be 1.9 inches. And its y bar is going to be, well, it looks like it's going to be right in the middle here. So it's 2.5 here, plus that 1.8. So that's 4.3. Now the area of it is going to be this 2 inches by this 5 inches. Okay, that's 10 inches squared. Okay, and again, I'm just going to go ahead and fill in the rest of this. Actually, I guess it really doesn't even need to pause, right? Because this is just going to be 19, and this one's going to be 43, right? With the one thing that we need to remember is that this area is negative, and these are therefore negative. Okay, so we're going to add all these suckers up. And we're going to get, what is this? 33.2 inches squared. This one's going to be 97.64 inches cubed. And this one's going to be, let's see here, 172.8 minus 43. And we try to do that in our head, and that's 129.8. Boom! 129.8. Okay, so then x bar, so these are the summations. Right, so then x bar, well, let's go ahead and get the whole thing. Let's label the whole thing here. So x bar comma y bar equals, we're going to take this one and divide by that. We'll take this one and divide by that. Okay, and so we'll get 97.64 divided by 33.2, and we get 2.9410. 2.9410, that's inches. And for y bar, we get 129.8 divided by 33.2, and we get 3.9096 inches. Okay, so before we continue, it's always a good idea to go back to your drawing and make sure that makes some sense. Okay. Looks like if our origin is down there on the bottom left. Oh, I don't want to erase that, right? Come on, you can do it. Anyway, so if our origin is in the bottom left, does it make sense that no, come on, you punk. Okay, so if our origin is down here, 0, 0, doesn't make sense that to get to the centroid of this thing, we'd have to go about 2.9 inches this way. So here's 0.9, here's another 2. So we're just barely on this side of that. And 3.9 going this way. So this is going to be what? 1.8. So we're going to have another 2.1. So maybe it'll be like, I don't know, somewhere up in here. So if I, kind of combine them, does it make sense that that would be the centroid? It's at least not completely outlandish. Okay? So we'll go ahead and leave it there, just as a reminder that, we solved for it. And it's about more or less right there. Okay, so now what we have to do is let's go ahead and box this off because that's a pretty important result right there. Okay, so now what we need to do is we want to find the moment of inertia of the whole thing. Okay, and so the way we do this is we're basically going to create another chart, and it looks a little something like this. Okay, so here's shape 1. Come on. Here's shape 2. Okay, and what I need for each shape is I need its moment of inertia around its own centroid, commonly denoted as like that. Okay, and we'll need that for both directions, I, y bar. We need the area. And I need the distance. Okay, and I'm going to create two distances. I don't really know what to call them. Let's call them distances in the y direction, distances in the x direction. Okay, and I'm going to go ahead and move, well, and I'll have one more, which will be a d y squared and a dx squared. Okay, so this is kind of a lot of stuff, but let's just do this one at a time. Okay, ix bar. So this is ix around its own, and iy bar around its own axis. Okay, or around its own centroidal axis. We've already solved for those for the big one. They're up here. Okay, so here we go. 230.4. Okay, this has units of inches to the fourth. This is units of inches to the fourth. This has units of inches squared. dy has units of inches. dx has units of inches, or d sub x, right? And then a d sub y, this is inches to the fourth, and this is units of inches to the fourth. Okay, most of y'all do not care about writing those in. It's a very bad habit. You should care. Okay, so iy then is 104.98, 104.98. Okay, the area of that big thing, okay, we can just look up here, and here's the base, and here's the height, so it's 5.4 times 8. So what is that, 43.2 or something like that? Let's go ahead and, oh yeah, we already solved for that too, didn't we? 43.2. Okay, now the distance y, so what that's asking here is what is the distance between the centroid of this shape and the centroid of the whole thing? Okay, we have the centroid of the whole thing. In fact, let's go ahead and just put those numbers in there. Come here, punk. You know what? It doesn't matter. Okay, so basically what we're doing is we're looking for the distance between, let's say in the x, like this guy right here, and this one right here. Okay, so in the x direction, that's going to be 0.2410 inches. And in the y direction, this number is going to be compared to that one. Okay, very close, right? I don't want to do that one. I kind of want to do that one in my head, but somehow I feel like I'm going to mess that up. So let's go ahead and use the calculator here. 0.09036. 0.0361. Okay. Notice in this case, I'm not worried about positive or negative here, you know, because this is the only column that matters, and I'm about to square all of that. So we're not going to worry about that. Okay, so we're going to go over here. I'm going to calculate a d sub y squared. Okay, so let's see here. The area is 43.2. I'm going to multiply it by times 0.090361. It's too many sig figs, but it's enough that we're going to be okay. Oh, sorry, we got to go back up. You have to be very careful here that you remember to square. Okay, and we get a very small number in this case, 0.35273. 5273. Okay, and there's a very good reason why this number is small, and it's essentially because this thing right here, especially in the y direction, is very, 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 very close to where the centroid of the main thing is. So the correction factor is very small for the fact that we're, you know, on a different axis, or for the parallel axis. Sorry. So the ADX squared. Okay, so this is going to have this 2.2410 business. So 0.2410 squared. It's also pretty small. And we're going to multiply that by 43.2, and we get 2.5091. 2.5091. Okay, so looking at these numbers here compared to these numbers, we can see the fact that the parallel axis theorem isn't really going to have much effect on the big shape in this case. Oftentimes that will be the case because the big shape is going to have the most effect on where that centroid is in the first place. Okay, so now we're going to do the second part, this little double bit, this little thing, and we've got negative values here, 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 and that's going to lead to having negative values here and here. Okay, so let's see here. So it's a rectangle, IX bar. Okay, and so this thing looks like this. And so if we want the x, well then in the x, this is our base, 2, and our height is 5. So we're going to have 1/12, 1 divided by 12, times the base, which in this case is 2, times the height, which is 5 cubed. Okay, 20.833. 20. Whew, terrible timing for an error. 20.833. Okay. For the IY, we're going to go, well, this is going to be my base, and the height is going to be 2, so it's going to be 1/12, 1 divided by 12, times the base, which is 5, times the height, which is 2 cubed, which is 8, right? So we're going to get 3.3333. 3.3333. All right. The area of that shape, well, we've already calculated that. That's a 10. Okay, dy, so that's the distance in the y direction between these things. So again, I'm going to... distance in the y and distance in the x. Did I get these right the last time? Anyway, let's go let's go ahead and solve this, and then we'll see if we did it. Okay, so 2.9401 and 1.9 will be 0.0... Oh, no, sorry. Let's not get carried away. Okay, 1.0410. Oh, that should be dx, shouldn't it? Okay, 1.0410. Okay, and so let's erase this. Okay, and then the y, we've got this number right here with respect to that number. So that's 0.4... oh man, give me a second. I'll use a calculator for that one. Okay, let's try 0.3904. Okay, like that. Okay, so the a dy squared. Let's go ahead and solve all this, and we'll check those numbers in the last line first. Again, so 10 area times 0.3904 squared equals 1.5241. 1.5241. That is a 5, although it doesn't really look like it. Okay, and we'll have 10 times dx squared, which is 1.0410 squared, equals 10.837. 10.837. All right, so let's, before we, finalize and finish this whole, this evening, let's check these numbers. dy is 3.9096 versus this number, 4.0. That's interesting. I think it is an error. Okay, well, I guess I surprised myself. I didn't actually make those errors. All right, so what we're going to do now that we've done all of that, okay, let's go ahead and, by the way, this is always easier if you don't have to do x and y at the same time, but I just, I am doing that, so we're just going to go ahead and do this. So the ix is sum. Okay, so we're going to have sums here, we're going to have sum here, we're going to have a summation here, and we're going to have a summation there. Okay, so we're going to say, well, 230 minus 20.833 equals 209.167, 209.17. Okay, and now, so that ix, okay, So that's going around, you know, we're trying, so we're using that to figure out, you know, the bending around this axis right here. So the distances that apply to are the distances in the y direction, going this way. So we want to know this summation right here, right? So we're going to do, let's see here, 0.35273 minus 1.5241 equals, okay, it's going to be negative 1.1714. Okay, so we're going to combine these two right here by just adding them together. Okay, and that's going to give us I x bar for the whole shape. Okay, equals, we're going to add 209.17, and we get basically 208. 207.99, or 208.00. 208.00. Okay, units on that, inches to the fourth. Okay, now we're going to do IY for the whole shape. Okay, and it's the same procedure, so I'm just going to pause it. Okay, and so we get a solution like that. And then, of course, we only want 3 sig figs, so we would go ahead and say that this is 208 inches to the fourth, and IY bar is 93.2 inches to the fourth. Okay, and if we want to compare those to our original estimates, which was that it was going to be a little bit less than 230.4, so that looks good, and a little less than 104.98, so that looks good. Okay, let's go ahead and look up, I'm going to go ahead and cheat and look up the answers and see if we got it right. And again, this disagrees with the book, but the book has to be wrong in this case, because they got answers for this one of 251 and 150, which are both above the object without the missing bit. So I don't know how they got that answer, because their solution is poor. So anyway, there's nothing wrong with the way that I did this. There might be a little math error somewhere in here, but you know, this is the right procedure. There's no question about that. You know, so I mean, unless I made an error right here, which I guess we should go ahead and check real quick, because that would throw it off. Let's go ahead and check that real quick. 1 divided by 12 times 8 times 5.4 cubed, 104.98. We're good there. And 1 divided by 12 times 5.4 times 8 cubed equals 230.4. Yeah, so somewhere in here the book made an error. It happens. Okay, so anyway, that's how you do it. I don't think I want to tackle this integral right now. I don't really like integration by parts. Yeah, I will try not to give you one where you have to integrate by parts on the exam. If so, I know what you're going to do anyway, or what I would do if I had access to the internet, is I would type this into the internet and get an answer. Okay, which in this case is fine, as long as you don't use another person. Okay, so anyway, hope you guys are having a good one. And I'm pretty tired. It's late. So I'm going to upload this, and you should have it tomorrow morning. All right. Hope you're having a good day. Bye.